Today we're going to talk about a very interesting example, Radix Sort. Radix Sort is one of the oldest sorting algorithms that have been used in various applications. It applies a divide and conquer strategy to basically divide the big problem into smaller problems. It splits data set into subsets and sort the elements in subsets, and it actually does this in several iterations. Radix sort is not to sort based on the values of the element. Instead, it sorts based on the digits of the elements. And we use the numerical representation of these digits. So we have naturally the least significant digits or the most significant digits. And we're going to perform radix sort along these number of digits in a sequence. And eventually we'll get the numbers sorted. Let's look at an example of radix sort. As we mentioned earlier, that the goal is to place the values into a small subset or subsets called buckets according to the digits. What we want to do here is to place the numbers into buckets according to the least significant digits. And then we're going to repeat the process using further significant digits. In this example, we have 8 numbers. And just for the sake of simplicity, we represent them in hexadecimal digits so that each number has 2 hexadecimal digits. For example, the first number is 52 in hexadecimal, and then 83 in hexadecimal, and so on. The goal is to sort these numbers in ascending order, and that is to say the smallest number goes first and the largest number goes last. So we're going to sort these 8 numbers. And in the first pass, we're going to sort based on its least significant digit. So what we are doing here is to look at the ones digit, well actually the least significant digit in these hexadecimal numbers. So we see here this number, first number is 2, and the second element has 3, and then third element has 1, and then so on. We have a knowledge about the least significant digit of all these elements. We're going to sort these numbers based on the digit on the least significant digit, and we're going to put them into buckets. And because we know we are doing the sorting on hexadecimal representation of these numbers, so in theory we have 16 buckets, whereas the first bucket are the numbers with the ones on the least significant digit, and the second bucket are for the numbers with 2 on the significant digit, and so on. So for these 8 numbers, we have hexadecimal numbers 31, 11, and F1. These 3 numbers are put into the first bucket. Then 52 is put into the second bucket, and 3 is put into the third bucket, and so on. Well, we don't have numbers ending with 4 or 5 or 6, but we have a number ending with 7 and with B and B. So as a result, what you can see here is that hexadecimal number 31 is placed before 11, although both of them are in the first bucket. This is because in the original sequence, it appears before the number 31 appears before the number 11. Similarly, when we look at the bucket holding these 2 numbers, 9b appears before 2b in the bucket for numbers ending with b, even though 9b is actually larger than 2b. We'll see that it does not matter for this case, for this iteration, because in later iterations, the orders of these 2 numbers or any numbers in the same bucket will be eventually sorted. To complete the sorting process, we will make another pass through the elements. But this time we're going to place them into buckets and depending on the next least significant digit. So what we're seeing here is we're going to look at the least significant digit, well, the second to the least significant digit, which in this case is actually the most significant digit. So 3, 1, F, and so on. So we're going to sort based on this digit and put them into buckets. So when we look at this, we are looking at these 1 because this is the most significant digit and it has a 1, and there's no other numbers as 1. So this is the number we're going to put into the first bucket. And we're going to look at all the other numbers as well, and we can find that this 2b is actually the only one that has 2 on the most significant digit. So this 2b will be put into the second bucket. And we move on, and we now found out that 3 is the only one with number 3 on the most significant digit. So this 3, 1 will be put into the third bucket, and so on. So we're not really sorting the values of these elements to be sorted. We're actually just looking at these digits. The final sorted sequence will be 1, 1, 2b, 3, 1, 5, 2, 9b, 8, 3, c7, and f1. And you can see that the sorting is done here. So what we did for this example is that we look at the least significant digit first, and we sort those numbers based on the values of that digit. We basically put them into buckets. And then we go through this process the second time to look at the other digit. In our case, it's the most significant digit because we only have 2 digits. And then we do the same sorting. We look at only this digit and sort these numbers by putting them into buckets. We never have to compare the values of these elements. The general rule is that if an element contains k digits, then we're going to have to go through this for k passes. That was the general approach of doing radix sort. What we want to show here is that each step of a radix sort is essentially a shuffle. The output equals to the input rearranged by a digit. And interestingly, OpenCL provides 2 functions. One is called shuffle, the other one is called shuffle2, and these 2 functions are actually very similar. These 2 functions will set elements in an output vector according to indices defined by a mask. And these 2 functions are quite useful for radix sort because radix sort is basically doing shuffle in different iterations. If we can have a mask, a very efficient mask, we can then rearrange the vector's elements with a single command. Let's look at this example. Just hypothetically, we have, let's say, 8 numbers, and these numbers are from 0 to 7, and these are the numbers we need to sort. And then let's look at this example. We have 2 vectors. One is called data, the other one is called ones. And in the first vector, we have 8 elements, and these elements are stored in one of these 8 locations in this first vector. And for the second vector, we have only 4 elements. We have 8, but in fact, we don't care about the last 4. So we have a few numbers here in the first 4 of these vector ones. And then we have a mask, which is a array of 8 elements. And the elements inside this mask array is actually, these numbers are the indices to these 2 vectors. And we count the indices from 0. So we have 0, 1, 2, 3, 4, 5, 6, 7. And from here is 8, 9, 10, 11. So let's look at the values in this mask. So we have 0, which means to generate a output vector, we're going to be getting the numbers from the location with index 0. So it's actually pointing to this location. So with this 0 in the mask, we're getting the value from this location and putting it into the output vector. The second element in this mask array is 4. So that is to say, we're going to look at 0, 1, 2, 3, 4, this 4th element, remember we're counting from 0. So this element, the value of this element, will be put into the output array here based on the mask, because we have 4 here. This 6 in this mask will similarly determine the value of this location in the output vector, but 6 will give us 0, 1, 2, 3, 4, 5, 6. So this is the location we're going to be finding the value from the original vectors. So this value 6 will be put into this location 6. Now let's look at the last one. The last element in the mask array is 11. So this 11 will be the index to determine the value in the output vector. So by using this 11, we're going to be finding, let's see from here, 8, 9, 10, 11. So this 7, the value in this array, will be used as the value in the output vector. So this is an example of how the shuffle function, and in fact shuffle2 function, works. We're going to define these functions more concretely. Shuffle function takes 1 or 2 input vectors and create an output vector that contains the components of the inputs. We mentioned earlier that we have 2 functions in this category. One is called shuffle, one is called shuffle2. The difference between these 2 functions are shuffle2 takes 2 input vectors, whereas shuffle takes only 1 vector. So what we're seeing here, in fact, from this definition and also the examples, is that we're not creating new values in the output vector, in a sense that we're just shifting or shuffling the original values from these input vectors based on the mask, and then create a new output vector. For both functions, you can see here, the very last argument is the mask, which determines the indices that we're going to use to build the output vector. Now, the mask has some interesting features that we need to keep in mind. The size of the components of the mask must be the same as those of the return vector. So if you want to have an 8-element vector return, then you expect to have an 8-element vector for the mask. But the data type of the mask must be an unsigned integer type. It could be unsigned character, unsigned short, and int, but you have to use an integer value, because these numbers will be used as indices to the original vector. The return vector will contain the same number of components as the mask vector. That's what we already know. And then the data type of the return components will be the same as the components in the input vector or vectors. So if your input vector is a floating point vector or integer vector, the returned the final output vector will be the same as the input vector. Only a select number of bits in the mask vector's components are important. Now it depends on how big or how many elements are there in the input vectors, and obviously only a small number of bits in the index value will be taking effect. Let's say if you have 8 elements in the original input vector, then we're talking about indices from 0 to 7, so only the last 3 digits will be significant, will be important, and the other bits above those 3 digits, binary bits, will be ignored. The value of k depends on the number of components in the input vector. For example, if you have n components, then k is log to n. This should be the base 2 log n, and of course on the other side, this n should be equal to 2 to the kth power. For shuffle2, the k is basically twice of the number of elements in the input vector, because we're considering 2 vectors. Let's look at this example. We're going to use shuffle instruction to create a float 8 vector from a component of float 4. Just to remind you that float 4 defines a vector that has 4 elements, 4 floating point numbers, whereas float 8 defines a vector of 8 elements, and each of them is a floating point number. So for this example, we're going to perform a shuffle operation, which takes the input vector and the mask. This input vector is shown here. It's a floating point 4, so we have 4 floating point numbers. And because 4 floating point numbers, we essentially have the index goes from 0, 1, 2, and then 3. The mask value here, we have a mask that is uint8. So that means this is an 8-element vector. So we have 1, 2, 3, 4, 5, 6, 7, 8 elements in this mask vector. But for each element in this mask, we have a value. Although it's int8, we're actually using only 2-bit of this integer, because the last 2-bit of this integer determines a value from 0 to 1 to 2 to 3. That is to use this values as index to select the corresponding element in the input vector. So in this example, let's look at the first element in a mask vector, and this value is 1. So this will tell us we can look at this index 1, this value here, and use it to put into this output vector in the first element. And the second element of the mask has a value 2. So we're going to be looking into the index 2 pointing to this location, and this will be the value that we're going to put into the output vector in this second location. And we're going to do this all the way to the very last element in the mask vector, which has a value of 3. So this 3 going to be used to find out the very last element in the input vector and use that value to build the output value in the output vector. So that's the very last location in the output vector. Now this is an example of shuffle 2. Shuffle 2 takes 2 input vectors, input 1 and input 2, with a mask. So what we expect to see is that we're going to have 2 input vectors. These are the original values, and then we have 2 of them, input 1 and input 2. In this example, all these input vectors contain letters. So we're going to expect a mask that's going to be using the values of these input vectors to build an output vector. And each of this input vector is 8, size of 8. So total together we have 16 elements in 2 of these input vectors. So what you expect to see is that for the values in the mask, we expect to see values from 0 to 15, because we are talking about 16 possible locations in these 2 input vectors. And the mask itself is a 16 element vector, so we expect to have an output vector that is of 16 elements, and the type of this output vector is going to be character, because each output element of this output vector is a letter. So we're going to be using the values in the mask to determine which value from the input vector we should use to build the output. Let's take a look at the first element in the mask. The value is 6. So we're going to find out the index 6, and so this goes from 0, 1, 2, 3, 4, 5, 6. So this will be the place we find the value, which is letter S. So this S will be put into the output vector in the first location here. And we can do the same thing all the way to the very end. So the last element in the mask is 13, and that is to say we're going to be using 13 as the index. So that's going to be in the second input vector, this location. So this value n will be put into the output vector as the last element. Here we put the shuffle instructions in a kernel function. This kernel function is named shuffle test. We take two arguments. One is the floating point number vector S1, and the other one is the character vector 16 element, and the name is S2. And then in this example, we have a mask1, which is a 8 element integer vector, and we're gonna be using a input vector that is 4-element floating point number and 4-element floating point vector, and the initial values are 0.25, 0.5, 0.75, and 1.0. And then we're going to perform a first shuffle function. In this example, shuffle function takes the input, which is this 4-element floating point vector, and the mask is mask1. So what we're doing here is, in fact, using this 8-element vector as the mask, and to build a output vector that has 8 elements, because we have 8 elements in the mask, and each of the element in the output vector is a floating point, because the input vector is a floating point. So this, in fact, performs what we showed earlier, the example, how we build an output vector with 8 floating point numbers using this 4-element floating point vector. In the second example here, we use mask2, which is 16-element integers, and we have 2 input vectors, and each of them is an 8-element vector that consists of 8 letters. And shuffle2 function will use these 2 input vectors and this mask2 to build a 16-element vector that consists of letters. So let's look at this example again. We actually saw this example earlier, but I want to use this example to explain how we go by sorting numbers in the kernel function we're going to explain. Let's say we have the numbers that we wanted to sort in this input vector data. And also we assume that we're talking about 8 elements, and these elements have values from 0 to 7. Now, we're going to be looking at how we can go with larger numbers, but let's assume that we only need to work with numbers that's less than 8. So with numbers that are less than 8, so we can use 3 binary digits to represent these numbers. Now these numbers will values that goes from 0 to 7, and we use 3 binary digits to represent them. So essentially we can look at these 3 binary digits one by one. Let's say we look at the least significant binary digit at first. So we're going to be looking at all these 8 numbers. What we want to do is we're going to look at these 8 numbers to pick out the numbers where the least significant digit is 1. Well, that is to say, we're going to look at the odd numbers. So it's not hard to find that we have this 1, 5, 3, and 7. These are the numbers which have 1 on the least significant digit. So we're going to be copying those numbers into another vector called ones. So as a result, we're not changing anything in this initial input vector. We only make the copy of these numbers in the new vector called ones. So that means all the numbers we didn't copy, these numbers 0, 2, 6, and 4, they have 0 on the least significant digit. Now, while we're doing this copy, we want to build a mask. This is very important. So while we're doing the copy, we want to build such a mask so that we will use the values in the mask vector to indicate which values are the values with zeros on the least significant digit, and which values are the values with 1 on the least significant digit. So let me explain this a little bit further. So let's say we are looking at these numbers one by one, and then this number 0, this value 0, if you look at this, the least significant digit of this number, we know it's a 0. So we're going to be putting 0 here to indicate that this number at location 0 has a 0 on the least significant digit. Now, for the second number, this number is 1. We know the least significant digit of this value is 1. So this value will be copied into this the second vector called ones. So the index of this number is actually now, instead of 1 here, is actually 8. So we're not going to put this index here. Instead, we're going to keep looking until we see a value that again has 0 on the least significant digit. In this case, this is 4. The index to this value is 4. So what we expect to see in this mask will be a 4 following this 0. This is to say that, okay, the first value that has a 0 on the least significant digit is at index 0, and the next value that again has 0 on the least significant digit is at location 4. And we're going to do the same thing to find out this number 6, which has 0 on the least significant digit, and its index is 6. So the 6 is the index of this value. And finally, this 4 is the number that again has 0 on the least significant digit. So the index of this number, which is 7, will be put into here. Now for the other set of numbers, the numbers that have 1 on the least significant digit, we're going to put their indices to the remaining positions. So we'll have 8, 9, 10, and 11. Now, you may wonder, why am I doing this? It turns out that if we can build such a mask, we can then use a shuffle to function to retrieve the values from the original vector and this new vector and build a new vector. So in this example, let's say we have these values in this mask vector 0, 4, 6, 7, 8, 9, 10, 11, and these are the input vectors. We're going to be pulling the value from the location 0 and put it to the first element of the output vector. We're going to then pull the value from index location 4, so this value 2 will be put into here, and then 6 and then 4. These values will be put into this output vector. And then we continue. We're going to pull value from this index 8, so we're going to pull the value 1 and then 5 and then 3 and 7 to this output vector. Now what we end up having here are basically numbers are put into 2 buckets. You can imagine this is the 0 bucket, this is the 1 bucket. The reason we have only 2 buckets is because we're considering binary digits, and so it's either 0 or 1. The numbers we put into the first bucket are the numbers with 0 on the least significant digit. And the second bucket are the numbers with value 1 on the significant digit. And that's how we do the first pass. And we can do the same thing. So this new vector here will be used to perform the second pass. And during the second pass, we're going to be looking at the second to the least significant digit. Now, here is the kernel function that we can use to perform the above operation. So this kernel is called Radix Sort 8. Sort 8 is just because we have 8 numbers we want to sort. And this global buffer, this global data is the input vector that we want to sort. Within the kernel function, we define a union structure. By the way, union structure here is similar to the union structure in C languages. That is to say that we're going to be using the same array of 8 short integers to use it as an array or as a vector. Either way, we can find the same numbers. And then we define 2 counters. One is 1 count, and the other one is 0 count. So these are the 2 counters that we're going to use to record how many elements that we should put into the ones buffer and how many we should put into the zeros buffer. This CMP value 1 is used to determine which binary digit we want to compare the values. And then we have 2 vector arrays, mask, ones, and data. And these, corresponding to the diagram we just saw earlier. So we have a mask vector, and then we have data vector that stores the original data that we want to perform the Radix sort. And then we have ones vector to store the values that we should put into the ones buffer. So also this data you can think about as the the zeros bucket. So ones vector is used for the ones bucket, and data is used for the zeros bucket. And then we assign the global data, which has all the values into this data vector. Note here, because this vector is ushort8, and also the input argument, this global data is also an 8-element vector. So you can expect that we're basically performing assignment of this whole 8-element vector to this data dot vector. And because data dot vector is a vector array, so we can also use it as a vector or as an array, either way that we can access these 8 elements. This for loop here goes from 0 to 3, so we're doing this 3 times. So we're doing this 3 times. The reason we're doing this 3 times is because we assume that the values are from 0 to 7, so we only need 3 binary digits to represent them. And so essentially this I will be determined by the number of digits that you want to sort. And this 0 count and 1 count are the counters to record how many elements that we should put into the ones array, or the other one is to indicate how many elements that we should put into the 0 bucket, or how many we should put into the ones bucket. We have a for loop, and j goes from 0 to 8, and we basically doing 8 iterations. That is because we have 8 numbers to be sorted. And we're going to take these 8 numbers. As you can see here, we're going to take every element from this data array. We're going to do a mask. We're going to do a logic AND operation with this comp value. And comp value in the first iteration, this will be a 1. And as we'll see later, that comp will be left shifted so that the next round, in the next iteration, we're going to be comparing the binary digit that's second to the least significant digit. And if that logic AND gives 1, that means we should put that value into the ones vector. So what I actually do here is we're going to make a copy of this and put that into the ones array, and then we're going to increment the ones counter at the same time. Otherwise, we will not do anything in terms of copying to the ones array. Instead, we're going to be recording the index, which is a j, put that into the mask. That's why you see here, if I go back to the previous slide, that's what we do here. We know that the first element, that the least significant digit of this number is a 0, so we should not put this number into the ones bucket. Instead, we should record the index, which is 0, into this mask vector. And then we do this for all the 8 numbers in the current data vector. As a result, by this time, you will have values, and the numbers that ending with 1 will be put into the ones bucket, and all the values that has 0 in the last least significant digit will be still remain in the data vector, but also their indices will be put into the mask array. And the next for loop is basically make the mask array complete. So we are doing here is to look at the remaining, because we're counting from the 0 count. So we're trying to find out how many values that are not in the 0 bucket. So in other words, how many values in the ones bucket. And we're going to be doing this a minus 0 count plus j. If I go back, this is really to build the remaining segments or remaining portion in a mask vector using these newly copied elements in the ones bucket. So we're going to be looking at this index 9, 8, 10, 11, and these will be in the remaining locations in the mask array. And then we're going to perform the shuffle operation. So it's going to shuffle using 2 input vectors, the original vector in the data and the ones vector that we copied. And then the mask dot vector are the values we put into the mask to indicate which values are in the ones bucket, which values are in the zeros bucket. Then we do the shuffle to build the output vector. And after that, we're gonna left shift 1 for one position for this comp value, so that in the next round, when we do this logic AND operation, we're actually gonna look at the second to the least significant binary digit. And eventually, we're going to have the sorted numbers in this data vector, and we're going to put these numbers back to the global data, which is in the global buffer. So that's the end of the Radix Sort.